Welcome. We often think of web search as a single magical act. You type a query and answers appear. But behind that simple interface lies one of the most complex, distributed systems ever engineered. Today, we're going to deconstruct that magic. We won't be covering the basics. Instead, we'll dive deep into the architectural decisions, the data structures, and the trade-offs that engineers at Google, Bing, or DuckDuckGo grapple with daily. Our goal is to understand the core principles of indexing and ranking that allow these systems to sift through trillions of documents and return relevant results in milliseconds. Let's begin. Before we get into specific components, it's critical to frame the problem around three competing constraints. First, scale. The web is not just big, it's incomprehensibly vast and unstructured. We're talking about hundreds of petabytes of data across trillions of unique URLs. Second, freshness. The web is alive. It changes every second. A search engine that shows yesterday's news is a failed product. This demands a system that can continuously ingest and process new information. And third, relevance. This is the most challenging part. It's not enough to find documents with the right keywords. The system must understand intent, context, and authority to rank the best answer at the top. Every architectural decision we'll discuss is a trade-off between these three pillars. The journey begins with crawling. This is far more than a simple script fetching pages. It's a massive distributed system of crawlers, or spiders, working in parallel. A central component is the URL frontier, which is essentially a sophisticated, prioritized queue of URLs to visit. This frontier has to manage politeness protocols, ensuring we don't overwhelm a single server, by respecting robots.txt and implementing adaptive fetch rates. A key challenge here is duplicate content. Hashing entire pages is inefficient. Instead, techniques like SIMHASH are used to create document fingerprints, allowing for near-duplicate detection at an incredible scale, preventing redundant processing and storage downstream. Once we have the documents, how do we find anything quickly? A linear scan is impossible. The solution, which dates back centuries, is the inverted index. Instead of mapping documents to the words they contain, we map words to the documents they appear in. For every term, we maintain a postings list, a list of document IDs where the term appears, along with metadata like the term's frequency and position in the document. This simple inversion is what makes sub-second search possible. Before indexing, text undergoes a rigorous normalization.